So common numbering systems, they talk about different numbering systems like, of course, decimal is our numbering system as far as counting to 10. Our money is in the decimal system. That's what we use every day. Binary numbers used in computers and PLCs. And a hexadecimal number is also used in computers and PLCs. And basically a hexadecimal number is, right on here, yeah, hexadecimal number is just another way of writing a large binary number, because binary numbers can get quite cumbersome, and hex numbers are just an easier way to write a binary number. When you start putting out a bunch of zeros and ones, you can, if you miss a 0 or a 1, you've messed up the whole number. Octal is another numbering system that's used in PLCs, and we'll get into the different types and why. The first PLCs only would have, I believe, 8 inputs and 8 outputs on their cards, and of course the memory size determined the octal system. And the older Allen Bradley PLCs, PLC 5, still use the octal system, while the newer stuff is back to the decimal system. It's based on a memory issue more than anything. So understanding these numbering systems can help you troubleshoot, especially if you're into PLCs. There's you can actually look in the logic or the data table for a certain device, input cards, output cards, and see based on whether it's binary or hex. You can set up little traps in the logic to do some troubleshooting. And of course, after this lecture and going through the module, you should be able to convert between the two. Now the module gets into a lot of detail that might be confusing, but I'll hopefully be able to hash that out for you and just try and keep it simple. You can do all these conversions on your calculator, and I'll show you how to do those. Clicker's not working. Let's try the next one. There we go. So what do we know about decimal numbers? Decimal numbers are what we call base 10. And binary numbers are what we call base 2. What do we mean by base 10? Decimal system uses 10 digits, and they are 0 to 9. So the radix or base is called 10. So we start with 0, count to 9 before we start again. The value of each decimal number depends on the digits that make up the number, and place the values of each digit. So maybe what grade did we learn this? Grade 1, we had the ones, the tens, hundreds, thousands, column, and so on, right? So million, 10,000. So 9 plus 1 equals 0. Carry the 1 to the tens column to make the number 10. Getting back into grade 1 here, right? Now in binary numbers, something very similar, but we only use 2 digits, and its radix or base is 2. What is base 2? The only allowable digits in binary are 0 and a 1. In a lot of cases, those zeros and ones represent if you have voltage or don't have voltage, on or off, high or low. Only uses 2 digits, so it only goes through 2 possible changes. So we can add binary as well as decimal. We can compare the two. 9 plus 1 equals 10. Adding binary, 1 plus 1 equals 10. And you kind of go like, what? Try and teach this to your kids. Since binary is base 2, when we add 1 to the 1, we change the 1 to a 0 and carry the column to the 2's column. So over here, this is the 10's column. Over here, this is the 2's column. So when we add 0 to 1, we get 1, and this is our decimal equivalent down below. We carry the 1. It looks like a 10, but if it's a binary number, sometimes I'll write a little 2 down here. Oops, that's not going to work. Let's try that. Just a little 2 to give you an idea that it is a binary number. A little more obvious when we see it later on. 11 plus 1, or 10 plus 1 is 11, right? So we have 1 in the 2's column plus 1 in the 1's column, which gives us the 3. And of course, 11 plus 1 is 100. What happened here is this is what we call the 4's column. So right now we have a 1's column, a 1 and a 2, 1 and a 2, and a 1, 2, 4. So as we go through this, you'll see a little pattern that comes up. So we have 1 in the 4 column and a 1 in the 1's column, so that adds up to 5. We have a 1 in the 4 column and 1 in the 2's column, which adds up to 6. So this is all our decimal equivalent down below. And of course, 4, 2, 1 adds up to 7. And of course, now our digit on the right there is our 8th column. If we compare that to a decimal number, that would be our thousands. That'd be our thousands, but here it's our 8s. Did you notice the pattern? Every time we carry 1 to the left, that column represents double the previous column. So it's called the least significant digit. So if we're looking at, say, the number 1 in decimal, that would be our least significant digit. Comparing that to, let's say, 100, this is still our LDS. This would be maybe our most significant digit. For binary, our binary system is from the right, least significant digit. So there's our 1s, 10s, hundreds of thousands places for decimal. For binary, it's 1, 2, 4, 8, and so on. 16, 32, 128, 256, 512, 1024, 2048, and on and on and on. So each digit in a binary system is known as a bit. For each, from the right, each bit represents a base 2 digit, doubling the previous column. So if 8421, it's also more. It keeps going and going and going to the left. So 1632 and so on. So we can take a 9 and convert it to binary, right? So we have 1 in the 8's column, nothing in the 4 and the 2 column, and 1 in the 1's column. So that's our binary representation of 9. 10 converts to 1010, and 11 converts to, we've got an 8, remember, 8, 4, 2, 1, adds up to 11. So 1011 is a binary representation of the decimal 11. So decimal numbers can be converted to binary and vice versa. There's our equivalent, decimal on the bottom, binary on the top, and so on. And we can convert 9, of course 10, 11, and 12. 8 and a 4 is 12. No questions you can't ask me unless you go and use your mic. I'll plow through, I can look later. Binary numbers can become quite large. So in your module, they start off with octal, but I started off with decimal and binary for a reason. And of course, now we'll go into hexadecimal. That just seems to make a little more sense for me, hopefully it will for you. Best way to represent a large binary number is to write it in a hexadecimal form. and it's a human-friendly representation of binary code, of course, used in PLC's computers and such. Hexadecimal system uses 16 digits, and they are 0 to F, right? Hey, something new, right? So if we looked at 10, basically we go to A, B, C, D, E, and F. So that's 16 places, right? But counting to 15. So its base or radix is 16. Decimal was 10, binary was 2. So 10 turns to an A, and so on, all the way up to 15. Since hexadecimal is base 16, the highest we count to before starting over is 15. And we can convert large binary numbers into hexadecimal numbers quite easily. Just got to follow grouping each digit into 4-bit groups. And we always want to start on the right, right? So there's a group of 4, and then another group of 4, and so on. Now here we have some zeros here that we ignore, but we still want to group them into that way in case we had another number out this way, because they're important. And then we follow our 8421, treating them as binary. That ends up being a 7. This ends up being a 3. 2 plus 1 is a 3. 8 and a 4 is 12. And a 1 is 1. Now the next step is, what's the 12 in hex? It's a C. We're over a C here. So this number here is the hex number for that large binary number. So this number here, 1110000111011, converts to 1C37H. So you'll also see it written as 1C3716 if it's a hex number. So just be aware of that. We don't usually write the 10 for decimal numbers, but if you see a little 2, maybe I'll see this as a 10 sub 2. That would be a binary number. And of course, we'd usually just use 10 for a decimal number, but this could be a hex, or also this could be a hex. So just be aware of that. I'll just explain that. So H, or 16. Let's give it a practice. So we'll break this into bits, 4-bit groups. 8421, so 2 plus 1 is 3, right? And 4 plus 2, or 8 plus 2, 8 plus 4 plus 2 plus 1 is 15. So you'll notice here all 4 bits high gives us a 15. This would convert to F3, and the H meaning that it's hex. 011 or 0111, right? That should be 777. Now, if we left it at 777 and didn't put our little h there, how would we know it was hex? So once again, it could be an H or a little 16 to give us that it's a hex number. This one, once again, break it down into 4-bit groups. I always start from the right. If we start from the left, if we have an odd number of, if we don't have exactly 4 in the group per section, then we could be in trouble. So I always start from this side, break it down this way. In this case, it wouldn't make any difference if we went the other way. But if we had less digits on the very last group there, then we could be in trouble. And of course, 8, 4, and 2 gives us 14, 15, 10, and 12. And of course, if we substitute the letters in there, we get cafe. It could be the word cafe, or if you got an H behind it, it is actually a number. Now on to octal. So octal is 8 digits. Octagon has 8 sides, right? So its radix or base is 8. And we only go from 0 to 7, so we don't use 8 and 9. So if we compare adding decimal numbers, 9 plus 1 is 10. When we add octal, 7 plus 1 is 10. Yay, good fun stuff, right? Since octal is base 10, when we add 1 to 7, we change the 7 to a 0 and carry the 1 to the next column, just like we did over here. So 7 plus 1 is 10. 17 plus 1, any guesses? Take 7, change it to a 0, and carry 1 over. It's 20, 30, 40, 50, and if you guessed the last one at 100, pat yourself in the back, right? Fun stuff. We can convert large binary numbers into octal numbers easily. So instead of grouping into 4-bit groups, 4 bits adds up to 15, 3 bits adds up to 7. We can break a large binary number into 3-bit groups. And so on. And you notice there the zeros at the front are basically irrelevant, but something to consider just in case we had another number out this way, we would have to, we can't ignore those zeros, right? So very far right, 7 or 3, 2, and 1, 7, 6, 0. We have to count them as 0, so 4 zeros are still a 0. 6 and 1. So this is our octal number of our binary number up top there. So this big number here converts to octal 160678 for octal. Sometimes you'll see a little O just mentioned there. So here we go, 3-bit groups. 3 to 2 is, or 2 to 1 is 3. 4, 4 to 1, excuse that. This should be a 6. 3, 1, 2, 4. Yeah, I think I messed up there. Yeah, I have to fix that. The number's right. Of course, a little 8. 7, 6, got it right this time. 5 and 3. Of course, the little 8 indicates it's an octal. Otherwise, you wouldn't know. 3-bit groups once again. Now you don't have to put zeros out the front here. They're irrelevant, but you might see it written that way. That's okay. 6, 7, 3, 5, 4, and of course 1. That's our octal number. There is no 8 and 9. Okay, now we can convert large binary numbers back to decimal. Now you don't have to follow this method. They explain it in the book. It's kind of cumbersome. On your calculator, you'll notice, let's just see here, I think I can put this on here. If you've got the 520, and I believe you have to be in mode 0 as well. Yes, mode 0. It won't work in mode 3. But you'll notice just above your times key, you have hex. And just above your divided by key, at least on mine, it might be a little different on yours depending on the model. You have bin for binary. And just below your plus key, or just above it I should say, you have decimal. And of course, just above your minus key, you have octal. And mine's in yellow, so in order to switch to those, you have to go second function. So in the 0, if I have a 0, normally on my calculator, a 0, when everything's cleared, if I hit the second function times, it will show up on my screen as a 0 with a little h over there. So that means you're in hex mode, right? If you go into binary, it will show up with a 0 with a little b, right? Now, don't confuse that b for a 6, right? And especially when you get into hex. And then octal, it puts a little o right up beside the 0. Now, there's another one on the bottom above the equal sign called the pen, and it is base 5. So that's something we don't get into, but it does exist. So you can follow this method, what I'm going to show you, to go from binary back to decimal, because what happens on your calculator is you can only put so many binary digits in there. And you might have a really large number and it won't fit. So you can literally break it down into 4-bit groups and enter it as a hex. Or you can break it down into 3-bit groups and fit it in as an octal and then change it to your decimal. So first off, we'll go first convert the binary number into hex or octal, up to you. 7, 3, 12, 1. But our hex number in this case is a C. Now our least significant digit is multiplied by 16 to the 0, right? So 16 to the 0, anything to the 0 is 1. Right, and then the next one over is going to be multiplied by 16 to the 1, and then 16 to the 2, and then 16 to the 3. And then you can add it straight up to get the total of 7223. So that's one way. The module shows you how to do it like that. Or on your calculator, you could just go back here. This would be 1C37. So you can put your calculator in hex mode by going second function times, and you'll see the little h, and then just put in the number 1. And as long as you're in mode 3, you'll notice above your CNST button, and the one beside it, at least on my calculator, is y to the x, and then x squared. But you'll notice just above there in green or a blue color, you'll see A, B, C, all the way up to F, right? D, E, F. Now you do not have to hit the blue key to enter that number. So as long as you're in hex mode, you can literally go up and hit x squared on my calculator, and it will give you on your screen 1C, and then you just put 37, hit your second function decimal, and you will convert it that way as well. So that's another option. If you don't have the 520 or a calculator that has those conversions on it, you'll have to do it the long way, which is a little more time consuming, but doable. Well, that's a long way. You could, on your calculator, there is, on mine, you can go y to the x. So you literally can go 1, oh, there you go in decimal mode, 1, and then hit the y to the x button. It'll put a little arrow like that, and then you just hit 3 plus, now put a 3 there, plus 12 y to the x, then a 2. It'll look like 12 y to the x. I might have to do brackets. We'll see what happens. 16 squared. Oh, I might have screwed up there. Yeah, I think I did. So 1 y 16 to the x. Oh, I have to mess around with that again, but you can do it with that button just to be sure, because you have to put that 16 in there. I'll have to mess around with that to be sure that's how it works. Yeah, that's how you do it. So you have to go on your calculator 16 times, or 1 times 16, then put your y to the x and a 3, and then plus 12 times 16 y to the x 2, and so on. And then your calculator will do it that way as well. So there's a couple ways of getting there. It's just best to use the simple method and just use the conversion keys. There's our conversion there. Practice. I mean, if you can fit the binary number in your calculator, you're okay. If not, you can just convert it to hex. Try it like this, or just put F3 in your calculator, and either way you should get the 243. 4-bit groups once again. You do it that way, or just enter 777 once you're in hex mode, hit the conversion to get 1911. Another one. You could do the long way, or what would 12 be? 12 in hex is a, let's see here, 10, 11, 12. So this one would be F, that's easy. This is E, 10 is A, BC, so cafe. Cafe, you can just type that in the calculator in hex mode and convert to this number as well, rather than doing the long method. Up to you which way you want to do it. I figure shorter number of steps in the calculator, the least amount of time chance for errors. A little bit of review. Base 10, what we use every day. Binary is used in computers, PLCs, which is basically industrial computer. Hex system is base 16, also used in computers and PLCs. And octal, the older PLCs, legacy Allen Bradley type systems. And of course, we can convert between the different numbers. Okay. Quiz. Okay, you guys don't have a quiz. You do have worksheets. So, but yeah, best to go through the module first. Now, a couple of things that I didn't cover in this is, let's see here, I'll open up this other page. I didn't cover ASCII or BCD. So that's just another little animal that it's good to know. It's in the worksheets that I got. But with a BCD number, so if we looked at, say, the binary number for 16 would be, if that's the ones column, 1, 2, 4, 8, 16. So this is our decimal number 16. This is the binary equivalent. The BCD equivalent is something a little different. Binary coded decimal, each digit can never go past 9. Right, so we still break it into 4-bit groups. So this would be, I need a 4 and a 2. Even though we have nothing in that column, we have to include it. And then, of course, this. So we usually don't write those zeros here. Just be aware that they are technically there because that one has to be broken down into a 4-bit group. So if we rewrote this number with just the 1, 1, 0, 1, 1, 0, then it looks like a binary number, but if you see BCD beside it, and that's what you'd have to have in order to know it's a BCD number or a binary coded decimal number, that's quite the difference, right, when you compare the two together. This being the binary for 16 up here, this being the BCD equivalent for 16. Another thing that the ASCII table you don't have to memorize, but basically the ASCII table is every time I type something on a computer or we put something in the computer, even this little drawing that I just did, it's getting turned into zeros and ones. Kind of mind-blowing, right? Put on a wireless signal on a carrier wave, sent over to you guys through the internet, and gets converted back into a number or text or a picture. Kind of blows your mind. So when you type an S on your computer, this is called ASCII. ASCII. And what's the actual? It's American Standard Code of Information Interchange is what that stands for. So when I hit S, the machine sees it as 1, 0, 1, 0, 0, 1, 1. And if I happen to hit T or spell the word stop, it would show up like this, or that's what the computer would see inside internally, because it's all just switched knobs, zeros and ones. Ooh, that was weird. Okay, 1, 0. That would be 1, 0, 0, 1, 1 to represent the O, and of course P. So that's the binary equivalent, or the binary number equivalent of the word stop, right? Which is kind of mind-boggling. But there's a whole chart on that in your binder on how that's converted. You have to memorize it. No, they do go into BCD though. They do a pretty good example. One thing where I think they fail at is where they don't show very well on how to go from one numbering system to the other in regards to dividing. I'll just kind of cover that before I let you guys loose to let you tackle it. What time are we at here? 10:13. Yeah, I think it's the one for octal. So basically they take 259. Now you can just do this on your calculator, but they just show you an example, just so you're not confused when you go through that example on how they're doing it. The first number, because it's octal, they divide by 8. That gives them 32 plus 3. You kind of go, okay, where the heck did that 3 come from? Right, but that's the 3 they put down below. And of course, use 8 for the octal. So if you actually do 259 divided by 8, you will get 32.375. So the 0.375 is actually 3/8. It's a portion of the eighth. So on your calculator, you do have an ABC key, and if you hit that key, it will rewrite your 375 as 32R. Oops, that's an 8. I need 3. And 3R8. So that's where that 3 comes from. right? And then they divide by 8 again, right? So 32 divided by 8 equals 4. And there is no remainder. So 0 remainder means we have to write a 0 there. And then we have 4 divided by 8 is 0, right? So if we go 4 divided by 8, there is no whole number. We get 0 or 0.5. Now this is where it's a little tricky. What is that in a fraction? It is a half. But what is that in eighths? We have to convert it to eighths. So it's a little messy. They don't explain it very well, but that's what's going on. So once again, best just to use your calculator to convert to numbers. And when your binary number doesn't fit to convert it to hex or decimal, just switch it to either octal or hex, and then go to decimal. Okay. I think that was it. Now they get into things like gray code and encoders and stuff like that. They show some different numbering systems there, but they're all very similar to binary. And we'll see how you guys are so far.